So in the last lecture, we talked about the basic structure of a time-dependent problem, and I showed you how to solve or how to implement a program that solves the heat equation. So at the time, we looked at a program that essentially just does the very basic thing. You set up a mesh, and then you solve the heat equation on this fixed mesh. Now, of course, deal.II is a library that is supposed to solve everything on adaptive meshes. And so what I would like to do is I would like to walk you a little bit through the process of how you would use an adaptive mesh for a time-dependent problem. You've seen this several times by now, how this looks for a time-independent problem, let's say for the Laplace equation in step 6. And you've probably taken a look at some of the other tutorial programs as well, where we solve some of the other problems. And basically, the structure of the run function of the primary function, where we do all of these things, looks always the same. So here now, I would like to do a similar process for a time-dependent problem. So our run function will have to deal with two things, namely refining the mesh and advancing the scheme time step by time step. And I would like to show you a little bit how this works. So there are a number of things that you have to watch out for when you solve time-dependent problems on time-dependent meshes, where you change the mesh adaptively with time. And I would like to walk you through some of these issues before we actually take a look at the code. So recall that we needed to solve an equation like the one at the top here. We used the theta scheme, right? So we replaced the time derivative by the finite difference approximation of the derivative, un minus 1 over the time step kn. And then we replaced the u by 1 minus theta un minus 1 plus theta un, and the same thing on the right-hand side. And of course, what I need to do at every time step is that I solve this for un, because un is the unknown that I still need to solve for at time step n, whereas everything that is on the right-hand side, in particular un minus 1, that is something that I already know from the previous time step, or because it's given, like f at time x and tn, or f at x and times tn. So I need to solve this equation on the left side, and I showed you in the last lecture how to do this. Now, let's come back to the issue of using different meshes at different times. So if you use a different mesh at time tn as opposed to time tn minus 1, then the finite element space is also different, right? I need to use different shape functions at time tn minus 1 as opposed to time tn. And so let me show this to you here. So if I expand the solution un here, so my solution un at time tn, I approximate that by a unh that I'm going to write like this. So it's going to have these shape functions phi j at time n times coefficients ujn. And if you remember the last lecture, these shape functions here were always the same, so I didn't have to write an upper index n here for these shape functions. All I needed is a phi j. But now, if I use different meshes at different time steps, then I need to use different shape functions at different time steps as well. So this approximation here for our solution u at time tn comes from a space vnh. And of course, I can do the same thing for the solution at the previous time step, right? So I want to write the solution at time tn minus 1 as I approximate it by a un minus 1h that I'm going to expand again in these coefficients with these shape functions here. And what I didn't write here is that the sum over j, of course, extends from j equals 1 to the number of shape functions I have at time tn minus 1 on the mesh at time tn minus 1, whereas over here, for example, the sum extends to the number of shape functions that I have on the mesh at time tn. So the size of these vectors un and un minus 1 does not even have to match. Now, if I do these expansions and I want to put this into the equation that I need to solve at every time step, so just to repeat, the equation that I need to solve at every time step is this one here, then as always, we multiply with the test function and we integrate by parts to get the discrete weak form. So I'm going to get something like this here, where on the left-hand side, out of this term comes a mass matrix, phi ni times, and here it is phi nj times these expansion coefficients u and j. I get plus theta k times the Laplace matrix here. And then I have over here on the right-hand side terms like this one. So this comes out of this term. I multiply it with phi n I at time n. And I get a term like this here, plus multiple other terms that come from the remaining terms on the right-hand side of the strong form. And let me look at this term a little bit more closely. So if I take the solution un minus 1h here, we have defined this as follows, right? That it is the sum over j of the expansion coefficients at time n minus 1 times the shape functions at time n minus 1. And so if you look at this closely, essentially what this means is that over here I have to integrate a product between a function that is defined on one mesh at time tn times a function that is defined on a different mesh at time tn minus 1. And if you think about this some more, it turns out that this is actually a really awkward term to integrate. Because if you were to write this down, when we integrate, we typically split our integrals over the individual cells, and then we replace the integral over individual cells by quadrature. And then when you do quadrature, you need to evaluate these functions at quadrature points. Now, if I split this integral, for example, into the quadrature or into the cells at time tn, then I get quadrature points on the cells on the mesh at time tn. And I know how to evaluate, for example, these functions phi I n on these quadrature points, or at these quadrature points on the mesh at time tn, because I know that the shape functions are just mapped from the reference cell to the cells at time tn. But I also have to evaluate the previous solution at these quadrature points. Now, the previous solution was not defined on this mesh. So suddenly I end up having to evaluate a solution at quadrature points that are defined on different cells than the ones that I had in the previous mesh. And so essentially what this means is that I have to evaluate a solution at quadrature points that are not mapped quadrature points on that particular mesh. Essentially, I have to find, or I have an operation like, here's the point, find me the value of the solution at the previous time at that point. And that turns out to be a surprisingly difficult operation, because essentially what it means is, because that quadrature point is defined on mesh at the mesh at time tn and not tn minus 1, I don't know which cell this particular quadrature point is in. Let's say which cell of mesh tn minus 1 this particular quadrature point is in. And so I have to go through all of the cells, find which cell the quadrature point is in, find what point on the reference cell this quadrature point corresponds to, evaluate the shape functions there, multiply it with these coefficients u, j, n minus 1, and that gives me the value of the solution u n minus 1 at that particular quadrature point. So this is a very expensive process. Trying to integrate shape functions from different meshes is something that is very expensive to do, and we certainly cannot afford that in general. So if you go back into the literature, let's say from the 1990s or from the 1980s, when people did this, they found that it takes them 50% or 2/3 of the time just to form the right-hand side integral of the equation, because it is so expensive to compute the integral of a shape function defined on mesh Tn against the solution of defined on the mesh at Tn minus 1. So it doesn't really work if you have completely independent meshes. So back in the 80s and 90s, people were using triangular meshes, and typically when you have triangular meshes, then one refined mesh is completely separate from another refined mesh. Essentially what they did is they just started a mesh generator at every time step and created a completely new mesh. In deal.II we do this a little bit different, and I think not just in deal.II, but we have learned today how to do this better. Namely, what we do is that we take a mesh that starts from a coarse mesh. Let's say just in the simplest case, a square. And you've seen many times how we refine a mesh. We split every cell in two in every coordinate direction, so in 2D we get 4 child cells. And then each one of these children may be refined some more. So that would be the way we produce a mesh at time tn minus 1. Now, how do we get a mesh at time tn? Well, we split some of these cells some more into children, and maybe we agglomerate some of the small cells into their mother cell again, if it turns out that the solution does not need to be on a fine mesh in a particular part of the domain. So that would be what we call coarsening. So through this process, essentially what we do is we end up with 2 meshes at times tn minus 1 and tn that have a very well-defined relationship to each other. That the mesh at one time step is a refinement, what we call a hierarchical refinement or coarsening of the mesh at the previous time step. And so if I need to evaluate the solution un minus 1 at the quadrature points defined on the cells at time tn, then there are only so many possibilities. Namely, if, for example, between every time step I allow exactly one level of refinement and one level of coarsening, then I know that the quadrature point on a cell at time tn will be within the children or the father or mother cell of the mesh at time tn minus 1. And so through this process, it becomes a lot simpler to actually do this. In particular, I can typically represent the shape functions on one mesh as a linear combination of the shape functions on another mesh, exactly. Which is not the case for triangular meshes that are not related at all. But for these hierarchical meshes, I can do this. The shape functions on one mesh are always linear combinations of the shape functions on another. Sometimes, if you refine it, then the shape functions on the old mesh are linear combinations of the shape functions on the new mesh, or the other way around if you coarsened it. So, through this process, we can make this integration of the solution of one time step against shape functions on another time step a lot more efficient. And if you want to see this in live action, there is an example called step 28 that does exactly these sort of things, where we deal with different meshes and we do the exact integration of one solution against the shape function on a different mesh. In practice, so it is possible to do this with these hierarchically related meshes, but I do want to say that it is, at the very best, I would say, awkward. It is certainly not an easy process. Now, if you look at this problem, it is something that certainly only becomes worse if you have multi-step time-stepping methods. I showed you these equations for the theta method. The theta method only ever keeps 2 solutions around, at time step tn and at time step tn minus 1. Many of the better methods, higher order integration methods in time, would have 3 or maybe 4 solutions. So not just solution at time step n and n minus 1, but n minus 2 and n minus 3 as well, for example. And in a case like this, you would have multiple solution vectors and potentially multiple meshes. And that process does not become feasible. I mean, doing this integration of the solution on one mesh against the shape functions on another mesh is clearly the right thing to do mathematically. This is what comes out of the formalism of the Rother method. But it is not something that is, let's say, practically feasible. And so in practice, what we do is that instead of integrating the solution on, let's say, the solution from the previous time step against the shape functions of the present time step, what we do is that we interpolate the solution un minus 1, so the solution from the previous mesh, we interpolate it to the current mesh, or project it, or whatever you want. Typically we interpolate it. So we get an object that lives on the current mesh, and then we integrate that against the shape functions that are also defined on the current mesh. So that makes it a lot easier, because if you have multiple time steps, just every time you change the mesh, you just transfer all of the solutions to the new mesh, and then you would just do the integration as if only one mesh had ever existed. So you can do this process while you refine the mesh. So let me show you the basic approach that we're going to do. So we are going to run our time integration loop. Whenever we decide that we want to refine the mesh, we do refine the mesh, we distribute the DOFs on the new mesh, we resize all of the matrices and vectors, we interpolate all of the solution vectors from the old to the new mesh. So in our case, there's only going to be the previous solution and the current solution. So that would be the solution and old solution variables in our class. There is a class that does this interpolation from the old to the new mesh that is called solution transfer, and I'm going to show you a little bit how that works. And then we build the linear system on the next time step Tn as if there had only ever been one mesh. So we never have to explicitly deal with multiple meshes. So this is the approach to the first problem that you will encounter when you have time-dependent meshes. Now, let me go through two other problems that you have to deal with. So the question is, when do I actually refine the mesh? Ideally, of course, you want to do this in every time step because the solution changes from time step to time step. But it turns out that mesh refinement is an expensive process, right? It takes us, if you think, for example, of step 6, if you measure this a little bit, you will find that this whole mesh refinement process takes maybe a quarter or maybe a third of the overall runtime. So you don't want to do it in every time step. But what you can do as a compromise is that you would do it every few time steps. So let's say every 5 to 10 time steps. That means that you amortize the cost. The cost of mesh refinement in that case will not be a significant fraction of the overall runtime anymore. And if you do it often enough, then that means that you still resolve the solution reasonably well on the current mesh. So often enough, but not too often. Then there's one additional complication compared to the time-independent case. So in the time-independent case, when you refine the mesh, you can happily refine into, let's say, a corner singularity. So in the time-independent case, you would just make the mesh as fine as is necessary, because there is no penalty for this. I mean, maybe the condition number of the matrix becomes a little bit larger, but by and large, there is no real penalty. For time-dependent problems, that is not the case. If you make the mesh too fine, then you will also have to make the time step much finer, right? We have this relationship between the size of the mesh and the time step. Certainly for explicit time stepping method, we have a very restrictive relationship between these two, namely the CFL condition. But for implicit methods, in practice also you want to make the time step smaller if you make the mesh size smaller. So we certainly want to make the mesh as fine as is necessary, but we don't want to make it too fine because that means that we have to take too many time steps. So in a case like this, what you typically do is that you limit the minimal mesh size. Let's say you allow yourself to have 5 levels of adaptive refinement, but not 6, 7, or 8. And in practice, what you also want to do is you want to make sure that every cell is refined, let's say, at least twice or 3 times, because it might be that something is going to happen in a part of the domain, let's say because a source appears, let's say a volcano erupts and there's suddenly a heat source. If your mesh is too coarse over there, you're simply not going to capture this. So in this case, you want the mesh to be, well, not too coarse globally. That is something that in practice doesn't hurt you too much. So whether your minimal mesh refinement level is, let's say, 1 or 3, there's going to be a few additional cells, but these are a few additional cells on the coarsest refinement level. And that's just a few dozen or a few hundred unknowns. That is not something that you should be too worried about. All right, so within these limits, within having a minimal refinement level and a maximal refinement level, the mesh, of course, can change freely. The last complication that I'd like to talk about is, well, what do you do on the very first mesh? So in the very first time step, you don't have a solution yet. And the question is, how do you choose the initial mesh in that case? So there's two basic approaches. The first one would be that you interpolate or project the initial values. Let's say you're given a u0 of x, the initial conditions. You project this onto the first mesh. You look at this and you refine based on this, and then you repeat this whole process, let's say 3 or 4 times. The alternative would be that you do the interpolation or the projection, and then you do one time step, and based on the result of this one time step, you would refine the mesh and go back and repeat the first time step. Which one you want to choose depends a little bit on the problem. So in the problem that we're going to solve in step 26, I have the initial solution is 0. The solution is exclusively driven through the right-hand side of the equation. So if I wanted to use approach number 1, where I look at the initial values and refine based on that to get the next mesh, it's not going to work because the solution is 0. So the only possibility in that case would be that I do one time step, I refine the mesh, and I go back and repeat the first time step on that. Okay, so that's what we're going to do. So with this, let me show you the modifications to the code that you need to do if you want to implement these sort of things. And what you will find is that the run function of this program has changed a little bit. I'm showing you this program essentially as a work in progress. So at the time when I record these lectures, step 26 is not actually finished. It is not linked in the tutorial. But you will get the basic idea, and maybe if there are some changes, you might have to look at the tutorial at the time when you listen to these lectures and look what has changed. So let me run you through the run function here. And essentially, the way it looks like, the way it works is like this. So I'm going to introduce 2 variables at the top of this run function that are going to be the initial global refinement of my course mesh, and then a variable that defines how many adaptive refinement steps I want to do in the very first time step. So in this case, I'm going to do 4 global refinements in 2D and 2 in 3D, for example, and 3 of these adaptive refinement steps. And then what I do is I create the course mesh, which in this case is just an L-shaped domain. I'm going to run this program in 2D. I'm going to refine it, this initial global refinement, number of times. Then I'm going to set up systems so that is distribute the UFs and resize the matrices and so on and so forth. Allocate some temporary vectors, and then I'm going to do something like this. So there's a label here that I will come back to. Then I interpolate the initial values, which in this case is just a 0 function. And then I have here my primary time loop. So this is essentially like it was last time already in the previous lecture. So I have this while the time is less than 0.5. And then from here all the way to, so from here to down here, this is exactly the same kind of code that we had last time already. So it is essentially the time integration where I build up the right-hand side and I solve one linear system with this. Output the results, and so here's the new part then. So I'm going to ask the following question. So if the time step equals 1, and I have not done all of the pre-refinement steps. I told you that I'm going to do 3 initial refinements for the first time step. So if I have not done them all yet, then refine the mesh. And the refine mesh function is going to have a minimum and a maximum refinement level that I pass to this function. I increment the number of steps that I have already taken, and then I go to the start of the time iteration. That was right at the top here. So I'm going to start again with interpolating the solution and starting the loop again. typically we teach students not to use go-to and labels. I think this is one of the rare occasions where you can make use of this because you want to have a jump back in time to a previous place in the function. And I think that is one of the rare occasions where it's legitimate to use a label and a go-to. Okay, so if this condition is not true, then I have another case where I might want to do a refinement, namely if the number of the time step is larger than 1 and time step %5 equals 0. So the percent operator is the modulus operator, which means, so I'm taking the remainder of the division. So that means if time step is 0, 5, 10, 15, and so on and so forth, then the result of this modulus operation is 0. So if this is the case, then refine the mesh. And in that case, of course, I do not go back to the start of the time iteration. I just set the old solution to the current solution and move on to the next time step. So this is actually rather straightforward if you think about it. The only function that we need to look at is this refine mesh function. And so if I look at refine mesh, that's a little bit more tricky. So what I'm going to do is I'm going to evaluate the error estimator with the Kelly error estimator like we've done many times before. And I'm going to set the refine and coarsen flags. That's also what we've done before. And then there's a little bit more. So here I have a loop over all of the cells. And if a cell is already at the highest refinement level that I allow, then I'm going to clear its refine flag. I don't know if it is set, but if it had been set, then it will be cleared for sure. So in other words, I will not end up with a mesh that is finer than the finest level that I allow, namely max grid level. And I do the same thing for all of the cells on the minimum level. Should they have a coarsen flag, then I want to remove that. And then I need to use this solution transfer class. So the solution transfer class takes a DOF handler, and I need to call a function that prepares the triangulation for coarsening and refinement. Essentially, it sets a few extra flags for refinement and coarsening, and then execute it. And because the solution transfer class, it stores the solution on the previous mesh, and when I refine it, in this call execute coarsening refinement, we call back into the solution transfer class to interpolate the solution from the previous to the current mesh. So then I call setup system, which means that I distribute DOFs, resize the vectors, and so on and so forth. And then what I need to do is I need to get back the previous solution to the current mesh. So I use a vector of vector here because I need to transfer both of these solution vectors, the previous and the old, and I get them back out of this temporary vector here. So that is really all that is necessary to take the solution from the previous to the current time step. All right, so just very briefly, because I have only 2 minutes left, let me show you what happens when I run this program. So I go to step 26. I say cmake minus d deal.II dir equals Bangerth bin deal.II dot. I compile it. And then I run it. So what you will see is that it runs the first time step on 768 cells. Then it runs the first time step again on 882 cells. It runs it again. These are the 3 times that we refine. And then it's done for good. And so from there on out, it does the first 5 time steps and then refines. So this is time step 5. And then it does the same thing on time step 6 to 10 on the next mesh, and so on and so forth. Out of the interest of time, I'm not going to show you the meshes that come out of this, but you can go to the step 26 tutorial program and take a look at how the meshes look like and how they evolve, and then you will see how this actually works in practice. All right, this was essentially what I wanted to say about time-dependent problems. basically all time-dependent equations will look like this when you implement them. You will have a loop over a few initial iterations, and then you will refine the mesh every once in a while. And that's the basic structure for this whole process.